Let's assume we have a subspace S in the n-dimensional space, and let's just assume it's not the origin. It contains the origin, but more than the origin. How do we define a basis? It's a collection of linearly independent vectors whose span actually equals S. That's the definition of a basis. A collection of vectors in S is called a basis of S if they are linearly independent and their span equals S. For example, in 2 dimensions, if your subspace is this line, then how many vectors do you need in the collection to span and be linearly independent? You just need 1. Yes, you just need 1. Because if you have a single vector which points this way, for example, if you take any linear combination of that, including 0, you get the span of the entire set. Okay? So, if R2 is your set, in that case, you will need 2 linearly independent vectors, so that any linear combination gives you the entire set. For example, these 2 will work. Okay. In the former example, any vector pointing this way, for example, will work because you can multiply it with a positive number and get all these points along this segment, and multiply it with a negative number and get all the points in the other reverse ray, and so you can generate all the points. The dimension of a subspace S is the following. Every basis of a subspace S in Rn has the same number of linearly independent vectors or has the same number of vectors which are by definition linearly independent and also whose span generates S. Okay? And this number is called the dimension of S. Examples. The dimension of the subspace Rn. Rn by itself is a subspace. Okay? It's actually a subspace, but it's not a proper subspace. By the way, maybe I forgot to mention, if S is a subspace, but S is not Rn. S is a subspace in Rn, but S does not include all points in Rn. And in that case, S is a proper subspace. Okay, let's just also use that term. So, in this case, the subspace under consideration is not a proper subspace. It's the space itself. What's the dimension of this? N. Okay? You need n linearly independent vectors, and you generate every possible vector in Rn by having those. What about the dimension of, for example, the set X in Rn, where X is a solution to the homogeneous system Ax equals 0. A is an m by n matrix. Okay? What's the dimension of this? Anybody? Say that again. 1? No, it's not 1. It's usually more than 1. Pardon? Rank of A? No. It's related to rank of A. N minus rank of A. The dimension of the space minus rank of A. Yeah, that's what it is. Anybody has any idea why?
Number of linearly independent utilities.
Okay. If you pick, since the rank of A, whatever it is, you can always pick, suppose the rank of A is, say, K, okay? Whatever it is, okay? Assume. So I can pick K linearly independent vectors from out of the columns of A and put the remaining vectors in some submatrix D. So this has K linearly independent vectors from columns of A. I'm partitioning A matrix column-wise with the first K being linearly independent. It's a basis. The remaining ones, n minus K, being the remaining columns. Okay? So when you do this, you can partition AX in the following way. So you've got B and D in partitioned form. You also partition your X vector accordingly. You put the variables Xj associated with the columns in B at the front. So XB has K components. And then you take the other ones and put them in XD. And you want 0. So this is BXB plus DXD equals 0. You're looking for a solution of this system like that. Okay? So, in solving this system, I'm looking for a vector XB, XD, where XD can be freely picked. So XD portion can be freely picked. And what am I supposed to have for XB when I pick XD in whatever arbitrary way? I should have here, well, if you just solve this, what do you get? You get XB equals minus B inverse. B is certainly invertible because it's got K linearly independent vectors. I'm assuming the row rank is also K here, okay? So you've got that. So if you put minus B inverse dxd for whatever, xd is free here, whatever it is, okay? So this will surely involve or will give you 0 because b times minus b inverse dxt will output dxt minus dxt plus dxt will give you 0. Okay? So here xt's are being freely chosen. So the set under consideration S in this case is the kinds of vectors, say xb, xt, in n dimension, where xb is defined by b inverse minus b inverse dxt. xt is free. It's any vector in Rn minus k. Okay, xt has n minus k components in it. So for this reason, this part is the free part. This part is a priori determined by your choice. And what is the dimension of this? N minus k, which is what we have. Okay, so it makes sense. Okay, what about the dimension of the set consisting of 0 only? The origin. Not 0, but the origin. 0, right? The dimension is 0. Okay, let's continue with orthogonality now. If you have two points in n-dimensional space, we say x is orthogonal to y, or y is orthogonal to x, it's symmetric, if their dot product is 0. Okay? And the origin is orthogonal . The other word for that notation is orthogonal. 0 is orthogonal to every x in Rn. Of course, we're talking about the origin here as a vector of zeros, okay? Because dot product of 0, or the origin, with any other x is 0. A point x or a vector x is orthogonal to a subspace S in Rn if x is orthogonal to every point y in that subspace. Okay? So point-to subspace orthogonality is defined by point-to-point orthogonality. For example, if you take the unit vectors 1, 0, and 0, 1 in 2 dimensions, of course they are orthogonal because the dot product will give you 0. And another example if you have, for example, a hyperplane like this with normal 1, 1. So these are the points 1, 0, 0, 1. And if you pick any point on the hyperplane, you will have orthogonality. For example, what's the equation of this hyperplane? x1 plus x2 equals 1, right? That's the equation. So there's a point x bar here. Give me a point on that. For example, which one? 1/2 and 1/2. Okay? So if you look at 1/2 and 1/2, and if you take it as x bar, it is in the hyperplane H. Okay? This is a point x. So if you look at x bar minus x, we get 1/2 minus x1, which is the first component of x, 1/2 minus x2. Is this orthogonal to 1, 1? Well, let's just try. Is it or is it not? It is. Because if you look at the dot product of the normal 1, 1 with this vector, you get 1/2 minus x1 plus 1/2 minus x2. And that's equal to 1 and 1 gives you 1 minus x1 plus x2. But x is a point on the hyperplane by assumption. So this part is also equal to 1, so you get 0. Okay? So obviously, for that reason, any point on the hyperplane relative to a fixed point on the hyperplane is normal to 1, 1, or orthogonal to 1, 1. Okay? If the dot product between 2 points x and y is less than 0, then the angle between x and y is greater than 90 degrees. Yeah. And if it is the other way around, then the angle between x and y is less than 90 degrees. Because x transpose y is defined by the norm of x, norm of y, times, was it cosine theta? Yeah, it was cosine theta. I forgot, but anyway, for that reason, whenever the angle theta between x and y is less than 90 degrees, your cosine theta becomes negative and you get that. Okay? Norm is always positive. Norm times a negative number. In the other case, you get, which one am I? Well, sorry. We are here. In this example, yeah, I should correct myself. Whenever the angle is less than 90 degrees, then you get a positive number for this, I guess. You know, this was from a long time ago. I don't quite remember, but it should be the case. So for that reason, you get this positive number. In the other case, you get negative, apparently. Okay? Let me write an important statement here. If S is a proper subspace, in Rn, meaning that S is not equal to Rn. So, if S is a proper subspace in Rn, then there exists a non-zero vector D in Rn, which is orthogonal to this subspace. Example. Well, before the example, let me also give you the following relationship. If the dimension of the subspace S is, say, M, which is, because it's a proper subspace, it should be less than N, okay? Then there exists N minus M linearly independent vectors that are orthogonal to S. So let me just do an example here. So we are in 2 dimensions, and we have a hyperplane. That's your set S, your subspace S. So M equals 1. The dimension of that set subspace is 1. In this case, there exists only one D up to a positive or up to a constant. Okay, you can have a multiplier in front of it other than 0. So D is orthogonal to this space. Okay. Well, let's take the same example in 3 dimensions. So we've got the same hyperplane. That's your S. This time we're in 3-dimensional space. So M is still equal to 1. Of course, in this case, I've got one like that, the other one going upwards. Okay? I can find 2 in this case. N minus M is 2. And this is orthogonal, say D1. This is a 3-dimensional vector, and this is D2. This is also orthogonal. Okay? It's going, it's going outside of the board. Okay? I don't know if the picture really illustrates that. Yeah, it does illustrate that. Okay? So if you have a line in 3 dimensions, you can always find 2 vectors that are each orthogonal to S. Okay? In higher dimensions, of course, you increase the number. Does that make sense? Some of you seem to be a little bit perplexed, but nevertheless, I think you can convince yourselves later. Yeah. All right, does everybody have it? Okay, first of all, let's understand what this theorem is trying to convey. We have S, a subspace, as a span of x1 through xk. And the dimension of S is assumed to be m. Then it turns out that there exists a basis of S consisting of m of the vectors x1 through xk. And part B, for any integer, positive integer j less than or equal to m, if you happen to have j of the vectors, and let's just assume by reindexing as necessary that they are the first j vectors. If x1 through xj are linearly independent, then we can build up a basis using those, starting with x1 through xj, and adding to that set some m minus j of the remaining vectors. Okay? Of course, making sure that the ones that we choose from the remaining set still fulfills the assumption of linear independence. You can always do it. It's all right, it's that type of a statement. How do you prove this? Well, first of all, part A is a special case of part B with j taken to be 0. Okay? So I will just go ahead and work on part B to prove B. So let x1 through xj be linearly independent by assumption. If any of the vectors in the remaining set, xj plus 1 to the last one, if any of the vectors xj plus 1 to xk is linearly dependent on the first j vectors, meaning that if you take any of the vectors xj plus 1 through xk and add it to the initial set x1 through xj, you have linear dependence. If that is the case, then the span of x1 through xj is the same as the span of the entire set. So if any of the remaining vectors, when adjoint to the initial set of j vectors, happens to be linearly dependent, in that case, of course, the span of x1 through xj is the same as the span of x1 through xk. You cannot generate something new anymore. Okay? Hence, x1 through xj is a basis for S in this case, because they are linearly independent and they span everything in S. In the remaining case, there is a vector in the remaining set, xj plus 1 through xk, which when adjoint to the initials x1 through xj, preserves linear independency. Okay? So in the remaining case, there exists a vector in the set consisting of xj plus 1 through xk such that if it is adjoined to the set x1 through xj, linear independence is preserved or maintained. Okay? So you've got one more additional vector adjoint to the initial set, and you still have linear independence. And adding it to this new set, this gives now j plus 1 vectors, one additional vector, that are linearly independent. Which brings us, of course, back to the same situation, except that j is incremented by 1 now. Okay? So you argue again, either the set of j plus 1 vectors on hand, they are linearly independent, and adding a new one to them will not preserve linear independence, or you just add one more. So you keep going. And so that does the job. Okay? You just use the same argument repeatedly until you finally end up with the former situation. An addition of new one will not preserve linear independence, in which case you already have obtained your span. Okay? Let's just briefly talk about column space and row space of matrices. So let's assume we have a matrix which is m by n. So let A be a m by n matrix. Column space of A is the set of all vectors that you can obtain by taking a linear combination of all columns of A. So the column space of A is the span of A1 through AN. Remember, I used this notation before. AJ, A sub j stands for the jth column of A. We did use that, didn't we? We did, yes, yes. So here AJ is the jth column of A. Okay, just for refreshing your memory. All right, that's the column space. What's the row space? It's the same, except that now you have the span of the rows. A super 1 stands for the first row, so on and so forth. You've got m such rows. So you are looking at the span of these vectors. A has full rank if the rank of A is the minimum of m or n. So either the row rank determines the rank of A, or, well, no, I didn't mean that. If, for example, the minimum of M in N happens to be, say, M, then rank of A equals M means you have full rank. The M rows under consideration, they are linearly independent. Okay? Similarly for the other case. If you take AX equals 0, the set of all such x's gives you the null space of A. The dimension of the null space of A is how much? N minus rank of A. Okay? Pardon? Ah, you're right. Yeah, it should be the column rank of A. Yeah. So suppose we have a subspace S in Rn, X bar is a point in S. Affine subspace and subspace, they are essentially the same things, except that as an affine subspace does not have to contain the origin. Okay? It's transformed by a constant vector. The origin is actually transformed by a constant vector. In this case, it will be X bar. So let's define the set denoted by S plus X bar. This is the name of a set. It consists of all points X plus X bar, all points of the form X plus X bar, where X comes from the affine, X comes from the subspace S. Okay? So you pick any point in the subspace, you add to it the fixed point X bar. Okay? And that's the new set. Such a set, or this set, is called an affine subspace. If X bar is the origin, of course, this is the same as your S. But if X bar is a non-zero point, then you have a new set. Okay? This new set, S plus X bar, may or may not be a subspace. As the origin is not necessarily in the new set. We define the dimension of S plus X bar as the same as the dimension of S. So the dimension of S is defined in a certain way. What was it? What was the dimension of S? the number of linearly independent vectors that generates every point in S, right? And you define the affine subspace obtained from S via translation by X bar in the same way, or you just define it to be the dimension of the associated subspace. Do we have a few minutes? Let me give you an example. So suppose S is the span of a bunch of vectors x1 through xk. In this case, the dimension of S plus x bar is, by definition, the dimension of S. And for this reason, it's the maximum number of linearly independent vectors in the collection x1 through xk. Another example. Suppose S is the set of solutions to AX equals B. So any x that satisfies AX equals B goes into S. What's the dimension of S? So to answer that, I'm going to pick some point which is a solution to AX equals B. So X bar is in S. Then a point X is in S if and only if AX equals AX bar, because AX bar equals B, which is true if and only if A times X minus X bar is equal to 0, which is true if and only if X minus X bar is in the set S prime, which is the set of solutions to AY equals 0. So S prime is the set of solutions to the homogeneous system AY equals 0. Okay? This is the null space of the matrix A. Okay? For this reason, S is the same as S prime plus X bar. So the set of solutions to AX equals B is obtained from S prime in this way. And of course, S is an affine subspace as S prime is a subspace. The solution set to a homogeneous system is always a subspace. Okay? So the dimension of S is the same as the dimension of S prime, which is, of course, equal to the dimension of the space. We assume everything is n space minus the rank of the matrix A. Okay? So this is how you can find it. Why don't we stop here, because we're already out of time and I think you are getting a little bit tired maybe at the end of the day. Huh?